Okay, what's momentum? Momentum is defined as the product of mass and velocity. So if you multiply the mass with the velocity, you will get momentum. And it's a vector. Let's slow this down. It's a vector and it has the same direction as velocity. So that means if an object is moving towards the east, what's the direction of momentum? Okay? Whatever is the direction of velocity, the same as the direction for momentum. And you know that the little arrow that you see on top of P, oh, by the way, what's the symbol for momentum? It's P, it's not M, because M is used for mass. So whenever you see the P, you know it's momentum. For lack of other letters that have already been used for some other things. So that's momentum, and momentum is a vector. What's the unit of momentum? You can take a guess before it comes up. Yeah, just put the units of mass and velocity together. The unit of mass, kilogram, and the unit of velocity is meter per second. So you have the unit of momentum as kilogram meter per second. Put them together. So you see that it's not kilogram divided by meter per second, it's kilogram times meter per second. Right? Okay. An example of a collision of an 18-wheeler colliding with that 18-wheeler is not moving. And somebody comes running and hits into it. It's funny. But you know who's going to be hurt. Although the guy was running, he had a bigger velocity. His mass was nothing compared to the mass of the 18-wheeler. You see, that truck was not moving. So now you start thinking that mass and velocity are equally important. Are you getting what I'm trying to say? Mass and velocity are equally important, so you multiply them and to get a new quantity. Now, does anybody remember Newton's second law? Do you remember Newton? You remember Newton's first law? Yeah. Third law, for every action there's an equal and opposite.
The second one is the opposite direction, right?
No, that's the third. The second one is net force is equal to mass times acceleration. I'm going to give it in a certain different way now. Watch this. Rate of change of momentum is equal to the force. Rate of change of momentum is equal to the force. So what do you mean by rate of change? Something divided by time. How much it changes with time. So rate of change of momentum is equal to the net force. You know that's the symbol for net force, isn't it? Sigma F is equal to delta P by delta T. What do you mean by delta P? Change in momentum. What's delta T? Change in time, because time always changes, right? So right there you have another formula for force. So you can calculate net force either using mass times acceleration or change in momentum divided by time. But I'm going to prove now that it's the same, that it's one and the same. Let's go back and see what we had written. Net force is equal to what? Change in momentum by time. But you know what change in momentum is? Mass never changes, so you're going to get mass times change in velocity, isn't it? It's the velocity that changes. So you get mass times v minus v naught divided by delta t. And what is v minus v naught divided by delta t? Acceleration. Why? Change in velocity divided by time. So you see how we get that formula. Now we have derived it. In the last chapter when we studied it, I just told you. But now we derived it. Is that making more sense now? Okay. The next very important thing is called conservation of momentum. Conservation of momentum. We're considering two objects here. Are they moving towards each other or away from each other, according to the diagram? On top. Okay. They're different objects. One has a mass ma, the other has mass mb. The one on the left is moving with a velocity va. The one on the right is moving with velocity vb. But you know what? After they collide, they bounce back. If you know what I'm trying to say, they bounce back and the velocities become va prime and vb prime. So they have new velocities. Okay? Now, who can tell me the total momentum before collision? What is their total momentum before collision?
MA.
Yeah, you have ma times va, that's the momentum of the first one, isn't it? And then you have mb times vb will be the momentum of the second one. So what's the total momentum before they collide? Add them up. MAVA plus MB VB. Correct? Pardon me?
The momentum will not change from before and after.
The total momentum will not change from before and after. The total momentum will be the same. If you take the momentum of each object, it would have changed. But if you add their momentas together, it will still be the same. Impulse. Have you heard of reflex action? Let's say that somebody pricks you with a pin from behind. You don't wait to see whether it's your dad or your friend or whoever it is. Immediately pick up whatever you can or your hand and bam! That's reflex action. Now, what's so important there is the timing. What can you say about the time involved? Is it small or big?
Small.
Really small. Now, how does that tie into physics? Just take the case of a tennis racket hitting the ball. What can you say about the time of contact between the racket and the ball? The time of contact. Is it small or big? It's really small. And what about the force? Remember, the force at the moment it touches is 0, and then it grows from there into a huge force, and then suddenly drops to a 0. All this happening in a very short time. Did you get what I said? It's like, or take the case of hammering a nail into a piece of wood. Same thing. Nobody ever hammers a nail like, no, you just, so the time of contact is small, but yet the force is huge, growing from nothing to huge and then falling. You have several examples. Kicking a soccer ball. Collisions, normally, all these are collisions that I told you now. Racket with the ball, hammer with the nail, whatever. So you cannot measure the force. You cannot measure the time because the time is too small. But you can measure the product. And that's what's called an impulse. So what's an impulse? Impulse is the product of the large force and the time for which it acts. So that is your impulse. A large force acting on an object for a very short time. That is an impulse. And how do you calculate it? I just told you. Impulse is actually the product of the force and the time. Force is a vector and the time. What will be the unit of impulse? Put their units together. What's the unit of force? Newton, and time is in seconds, so the unit is Newton second. Some examples. Shock absorber. What does the shock absorber underneath a car do? Does it make the time bigger or smaller? Think about it. If there were no springs under the car and you fall or you hit something, what's going to happen? You didn't get that force on your spinal cord, isn't it? What does the spring do? It makes the time a little bit bigger. Correct? Thereby the force becomes small. Try to understand. Because the product is going to be the same anyways. If you make the time bigger, the force becomes. Or let's say that you are jumping down from a tall building. Never do that. Never attempt it, please. But in case you have to, not so tall, the best way is to bend your knees when you land. Does that make sense? If you don't, you'll have a pair of broken legs. But if you do bend your knees, what are you doing to the time? You're increasing the time. And what are you doing thus to the force? Decreasing. Is it making sense? You increase the time, the force decreases. There are several, whatever I could think about, I've written here. Second one is bending your knees, pulling your hand back when catching a fast ball. That's good. In baseball, nobody catches a ball like that. That's the last time you'll catch it. Even if you have gloves on. What you do is, you catch it. See, what are you doing to the time again? You are prolonging the time, thereby making the force small. You can find a million examples of this. Increasing the time to reduce the force. In one dimension. Wait. What do you mean by collision in one dimension? Watch this. If you have two objects moving along the x-axis, and after collision they continue moving along the x, that's collision in one dimension. But is that always the case? Couldn't you have this? Watch. Couldn't you have two objects moving along the x and then one goes off that way, another this way? That's collision in two dimensions. You can even have a worst case where one of the objects breaks into two pieces. One flies up. Are you watching what I'm saying? One flies up. The other goes that way. The one that hit goes this way. So now you have the x, you have the y, and you have the z. Anybody got it? We will not get to there. We'll just study one-dimensional collision and get some formulas. This is the last piece of concept for today. Okay, so we're going to derive something. We already know the momentum will be conserved, isn't it? What's the formula that we get? Write that down, please. Try to write this. MAVA plus MBVB is equal to MAVA plus VA prime plus MBVB prime. And then, there are two types of collisions. One is called an elastic collision. The other is called an inelastic collision. We're going to talk about an elastic collision. What is an elastic collision? Where the kinetic energy, oh, by the by, do you remember kinetic energy? Or what's the formula for kinetic energy? Okay, half times mass times the square of the velocity. If the kinetic energy is also conserved, then it's called an elastic collision. So the total kinetic energy before should be equal to the total kinetic energy after. Anyways, momentum is always conserved, but if all kinetic energy is also conserved, it's called an elastic collision. Okay, so for an elastic collision, you can also write the formula that's coming up, the equation. What's the kinetic energy of the first object? 1/2 times, come on now, 1/2 times MA times VA squared, isn't it? Plus, what will be the kinetic energy of the second one? 1/2 times MB times VB squared. Come on. That's what I'm writing. All right? And that should be equal to 1/2 times MA VA prime squared plus 1/2 times MB VB prime squared. You understood what an elastic collision is, isn't it? Kinetic energy is also conserved. Now for some math. If you go to the first equation, and we can rearrange it, I'm talking about the first equation. Got it? Not yet?
Yes, you
Oh, hold on. Let me finish. And then I'll. Now go back to this equation. Do you know that in algebra, a squared minus b squared can be written as a plus b times a minus b? That's what I'm doing. So I'm breaking up this quantity there into VA minus VA prime plus into, right? Okay, do the same on the other side. Do the same on the other side. So that becomes VB minus VB prime times VB plus VB prime. And then I'm going to call this equation 1. That's equation 1, and this is equation 2. And I'm going to divide 1 by 2. Your questions should wait up to the end. Divide 1 by 2. If you divide 1 by 2, do you see that some of the terms will get cancelled? What terms? Let me cancel it for you right here. You're dividing 1 by 2. That's there for everybody to see. What's going to happen to the MA? Cancel out. What's going to happen to the MB? Cancel. Isn't it? Actually, I had to cancel it from here. Sorry, from here. And then don't you think that this will get cancelled with this one? Because you're dividing. And this gets cancelled with this one. And you're left with? Yeah, you're left with this thing, which I've written. Look, that's the only thing that remains when you divide 1 by 2. Therefore, if you rearrange that, you take VB to the other side, it'll become VA minus VB is equal to VB prime minus VA prime. Even if you don't cram the whole method of derivation, you need to remember the last one because that's really important. This is the important equation right there. VA minus VB is VB prime minus VA prime. And that's, did you notice that it's the other way around here? Oh, you didn't? Okay, time for questions.